Okay, so welcome to our webinar. This webinar is dedicated to the zero-U water propulsion system. And our first slide is about SatRevolution and our history of our missions at a glance. We've been established in 2016. Our first satellites, 2 satellites, seen the orbit last year in 2019. We're building a few missions now, including the one for our partners at SteamSat, their tech demonstration mission. And by the end of this year, we should have a total of 7 CubeSats in orbit. Our big aim right now is the launch of the first stage of our constellation in 2023. And we're specializing in Earth observation technologies. Next year, in 2021, we're having a couple of shared missions with optical capability. So if anyone's interested to join, you know where to find us. And with this, I am passing the word to Marco of SteamJet.
Hi, Gleb. Thank you very much for inviting us, for hosting us today. So good afternoon, good morning, or good evening, depending where you are in the world. My name is Marco Pavan. I am the business developer and the co-founder of SteamJet Space Systems. And as Gleb introduced already, I'm going to talk about our zero-unit water propulsion system. So if you can go to the first slide, please. First, okay, a bit of introduction about SteamJet. The company was founded in 2017 with the aim of developing a safer, more compact and affordable propulsion system for CubeSats and for small satellite. We have at the moment 8 people working at this project. We have an office in UK and we also recently opened an office in US. Here in UK, we received over £100,000 in grants and funded projects from the UK Space Agency, from the Spring Program and the European Union. And we also set up already testing collaborations with several test entities here in UK and also with the University of Southampton to do the qualification of our propulsion system. Next slide, please. If we look at the size of a typical satellite 20 years ago, it looks like something that we can see here on the left part of the presentation. It was something extremely big. It was as big as a car or even more. It was weighing thousands of kilograms. It was costing hundreds of millions and taking more than 5 years to be developed. And these satellites were used, for instance, to do Earth observation, so to take pictures of the Earth or to monitor the Earth atmosphere or with different other payloads, do other Earth observation things. However, the same mission today can be done by something which is extremely different. If we look on the right side, what we can see in the circle is a free unit. And free units can be used today, is a free unit CubeSat. And those kind of satellites can be used today to do Earth observation, so taking pictures of the Earth with a resolution which is actually higher than what it was available 20 years ago. And these smaller satellites obviously are also less expensive. A free unit usually costs less than $1 million to be developed. And they have a mass of around 10 kilograms in this case. Their size is not as big as a car, but it's more shoebox size. And finally, they're also much quicker to be developed, 1-2 years. Next slide, please. However, propulsion systems which were designed for large satellites are not really suitable for CubeSats and small satellites. And this is because of the small size, but also because of the strict safety limitations. So CubeSats and CubeSats usually are considered as a secondary payload. Therefore, they can't really introduce any big risk on the mission for the primary payload, which is the big satellites, which is paying most of the cost for going into orbit. Therefore, CubeSats and all their subsystems can't really they can't really use hazardous or hazardous propellants or flammable propellants and pressurized tanks. And also, if you have your CubeSat, which is deployed from the International Space Station, for instance, then you can't have a propulsion system which are using hazardous propellants or pressurized tanks, because they can't be stored within the International Space Station. But if you don't have any propulsion on board, then you will end up having a very short lifetime, for instance. So if you launch your CubeSat on a orbit, which is the ISS orbit, again, like the International Space Station orbit, around 400 kilometers, then your lifetime will be about 1.5 years. So very short. And also you can't really perform any orbital maneuvers without an active propulsion system on board. So you can't really optimize your orbit. You can't deploy your constellation. So you can't phase the satellites into your constellation orbit. You can't avoid collision. We all know that there are more and more space objects now into orbit. And it's the chance of being in a collision with another space object are increasing. So without propulsion, you can't really change your orbit in case of collision. And finally, you don't have the orbit capabilities. If you are in an orbit over 600-700 kilometers, then your satellite might be orbiting Earth for more than 25 years, maybe centuries. And this is violating the Re-Entry International Guideline, which tells you to bring back your satellite basically within 25 years. Next slide, please. So this is why as SteamJet, we decided to use a propellant which is completely safe, which is non-toxic, non-flammable, and is low pressure. This is why our proprietary technology uses just low pressure water as the main propellant. And this massively reduces the cost and the risk associated with the other typical propulsion systems, such as cold gas thrusters or chemical systems. And because we use only low pressure water, then we can have a very low risk. Our system is introducing a very low risk in the overall mission, and also is very easy to integrate into the satellite. It's basically 4 screws plus a plug and play connector to the satellite bus. Next slide, please. So I would like to spend just a few words about our first product, which is the Tuna propulsion system. So the Tuna unit is the only propulsion system that can be actually installed outside the main CubeSat structure, because we are exploiting the so-called Tuna volume, which is available in CubeSat deployers. We can see on the left side the typical configuration with a CubeSat and a CubeSat deployer, which is around it. Now there is a volume which is taken by a spring in the deployer. That spring has the purpose of pushing the CubeSat outside the deployer into the final orbit. Now we designed the propulsion system in order to take benefit of that volume so that we can fit the whole propulsion system in there. And in this way, we don't take any volume inside the CubeSat structure. And this obviously leaves more volume inside the CubeSat for bigger payloads or other subsystems. Next slide. Please. So as we can see on the left, that is our Tuna propulsion system. It's a fully contained unit, which includes the thruster head with the exchanger, the electronics, and all the control systems, and also the water tank with the propellant as well. If we take a look at the performance, then we can see that that fully contained unit, which again is installed completely outside the structure, can provide thrust over 6 millinewton. And this is 10 to 50 times more than what can be delivered with electric propulsion systems. Having a higher thrust allows to the propulsion system, which is not generating any revenue. And in terms of specific impulse, at the moment, we are over 170 seconds, but we believe we can actually do better than this. This unit delivers around 219 Newton seconds in terms of total impulse. And I will show later what you can actually do with 219 Newton seconds. The other important parameter for us is the power consumption, because this unit needs less than 20 watts basically to operate during thrusting. And this is less than half of what is required by typical propulsion systems, which are around 40 to 50 watts. And finally, in terms of dimensions, so as I said, we designed this with the purpose of using the Tuna can volume, which is the largest Tuna can volume is basically 80 millimeters in diameter and with a depth of up to 80 millimeters. So that is the side basically of our propulsion system. Now, if we go to the next slide, we can see that we also have different options. So in case you need more total impulse because your mission requires, let's say, a higher delta V, then we can have different options, which are the Tuna can Plus and the Tuna can Plus Plus. The performance in terms of thrust, specific impulse, and power consumption are the same. However, with the Tuna can Plus, we basically carry a water tank with the size of 1 unit inside the satellite, and the Tuna can Plus Plus has a water tank which is 2 units basically inside your CubeSat. So that obviously depends, as we can see on the right, what is your delta V budget and how much actually water you need to carry for your mission. In terms of dimensions, in this case, we're not taking the whole Tuna can volume. We're using 80 millimeters in diameter, but just half of the large Tuna can volume in depth, so up to 40 millimeters. And then we have 1 or 2 units of water inside the satellite. Now, if we go to the next slide, I wanted just to give you an understanding about possible applications. So if we consider the first case, which is a 3-unit CubeSat, 5 kilograms in terms of mass, and an initial orbit of 400 kilometers, which is the International Space Station orbit. If we don't have any propulsion on board, then our lifetime, as I mentioned, obviously you cannot do any orbital change or adjustment. They hit another object. If we consider just the Tuna can system, which again can be installed completely outside the CubeSat structure, which is delivering 219 Newton seconds, well, what you can actually do with that is already quite a lot, because you can extend 3 times your lifetime. From 1.6, you can have up to 4.3 years. So you can actually extend it almost 3 times. Plus, you can have orbital changes. If you need to optimize your orbit, you can have up to 70 kilometers. And most importantly, you can do orbit phasing. So if you have a constellation of 3 units, then you can easily locate and phase your satellite along the constellation orbit using just the Tuna can system. And finally, you also have the possibility to do collision avoidance in case you need it. And if we consider the case of a 6 unit, which is in this case obviously heavier, it's 10 kilograms in mass, same orbit, then we can see that with the Tuna can, you can still achieve good performance in terms of lifetime. You can have up to 3 years. You can do very small orbital changes, so possibly just some adjustment. You can do orbit phasing, so phase your satellites. You can possibly deploy a constellation just with the Tuna can, and you can do collision avoidance as well. But if you need to actually have bigger changes, then we would advise to go with the Tuna can Plus, which carries more water, therefore it can give you a total impulse over 1,000 Newton seconds which is actually similar to an electric propulsion system of the same size. And obviously you can do bigger orbital changes and phasing and collision avoidance, as we saw earlier. Now, next slide, please. The technology level of our Tuna propulsion system is TRL7. So the system has been extensively tested here on Earth, but we are really excited because we have our first in-orbit demonstration, which is planned for December 2020. So we are gonna use our own SteamSat-1, which is a very tiny 1.5 unit CubeSat, which is supplied by SatRevolution. And we're going to test the system on a sun-synchronous orbit between 500 to 600 kilometers using a Falcon 9 vector and shuttle service from Momentus, which is the Vigoride. Now, if you go on the next slide. Now, before finishing, I just wanted to give you also a bit of overview about what are we going to achieve in the next years. So the main core of our technology is the steam generation technology, which is how we basically convert water into steam using very little power in a very compact design. The Tuna thruster is the first product that we actually developed, and that is designed mostly for small CubeSats from 2, 3 units to 12 or 60 units. But our same technology can be scaled up and applied to bigger satellites. So we have a built-in thruster tank, which is thought for small satellites up to 150 kilograms, and that will be ready in 2022. And finally, also, we're applying that technology to provide attitude control. So that will be used to provide attitude control, not just to small, but also medium and large satellites as well, to provide a good alternative to hydrogen or cold gas thrusters used today. So that will be around 2023. Next slide, please. I think it's the last one. Yes, so just want to say that the Tuna thruster will be available for delivery from 2021. And thank you very much, everyone, for listening. Thank you, Glebe and SatRevolution, for hosting us. And if you need more information, if you want to contact me, that is my email. Feel free to visit also our website, steamjet.space. And I'll be also happy to answer any question now after this presentation. Thank you.
Thank you very much, Marco.